So my colleague Jungchi already gave you like a very brief introduction of Lumerical simulation using So using this finite time domain, finite difference time domain method. So he usually talked about how we can couple the light from the bus waveguide to the resonator. So how we can really optimize our design to decide what is the gap distance between our bus waveguide and the resonator. But I will mostly talk about how we can couple the light from external source using optical fiber to our photonic chip. This is very important because it's like the more the light we can couple to the chip, our system will have more power efficiency. So our overall efficiency of the system will improve. So because nonlinear photonics already takes quite a lot of power for the different nonlinear conversion processes. So if we lose power only towards from just coupling from fiber to the chip, so then we have to pay quite a lot of overhead on this side. Just to connect, because this workshop is just related to the MICROCOMB, so I just give you a different platform that are chip based. The reason for giving you the chip based MICROCOMB platform is to tell you that a lot of platform used for the micro resonator frequency comb generation are chip based, such as in our group we mostly focus on the silicon nitride. Similarly, this platform is also used at the group of Alex and Lipson at Columbia. Similarly, recently the group of Professor Kariuhala came up with this wedge resonator that are coupled to integrated waveguide. So we really need to couple light externally using optical fiber. Some other platforms such as aluminum nitride or gallium phosphide, lithium niobate. So as my colleague mentioned, that how we can really optimize this gap distance, how to couple the light from this bus waveguide to the resonator. But my talk will be like how we can couple the light from this externally from fiber to this bus waveguide. So the whole idea will be to make a system that is very efficient, and we can make a much better mode converters. So it's not about only chip based version, but if you see like a non-chip based micro resonator, such as a recent work done by my colleague Miles, you see like conventionally people for the crystalline micro resonator, they use this fragile taper fiber. So there's a piece of fiber, you try to pull it, and then using evanescent coupling, the light was coupled in and out of this crystalline micro resonator. I mean, because this type of platform is not very usable for photonic integrated community, so you can only do this type of experiment within the lab. So if you want to do some experiment out of the lab, you really need to make a photonic integrated system. So for this, I think our group has came up with this nice idea of coupling light with the photonic chip. So a bridge waveguide was designed to couple light in and out of this micro resonator. So that already shows you that why coupling the light to the photonic chip is very important. So, but why there is a need of mode converter? So most of the platform that I already showed you in my last slide, they have a high index. So they have a high index, let's say more than 2 or 2.5. So the contrast between the cladding and core is more than 0.5. So it means they have a high index contrast material, and waveguide is the mode is confined very well inside this waveguide. So if you take an example that if we don't have any mode converter, we have just a waveguide section. So you will have a mode. I mean, this is just for a picture, like a graphical representation. So mode is very well confined inside this waveguide. And if we try to couple with the lens fiber, not with the standard SMA fiber that has 10 micron of field diameter, so you will see that the mode overlap is not very good. And if we see the coupling efficiency equation, I mean, this is just a mode projection or the orthogonality relation. The coupling efficiency depends how the mode of your optical fiber mode and the waveguide fundamental mode overlap. And you can clearly see the overlap is not very good. It means like we can just couple like maybe less than 5 or less than 10% of light from our external fiber into the chip. That's going to degrade our overall efficiency of our system. If you think about, then people came up with some nice idea to make a mode converter on chip. So if you see like a very nice, what they did basically, if you try to move toward the chip, then the size of waveguide is reduced. So now what will happen? Your mode is not more inside, is not inside the waveguide, but rather start seeing the cladding more. And then what will happen? It start becoming bigger. So you can think about the effective index start reducing, and your mode size start becoming bigger. So what will happen now, this mode and this mode will overlap perfectly, and we have a very nice coupling efficiency. The things we really need to care about is how the mode is overlap at this point with your fiber mode, and also how we are going to convert this mode into the waveguide mode adiabatically. So these two things we really need to take care about. So what is the mode size at this point, and how we are going to design this taper such that mode adiabatically convert into the waveguide mode without losing the power. So so that's more like the kind of motivation for us to really make some mode converter on the chip, such that we can couple the light with better efficiency, with better efficiency to the chip. So I just put like a small list here, so to show you like what kind of existing mode converter solution people already built. So the first one I already show you is the inverse taper. The advantage is that it works for very broadband wavelength. So you can really make a taper mode converter that can cover the range around 1 micron to 2 micron easily. Then there is a grating coupler, so you can make this nice periodic waveguide structure. The advantage of this thing, you can use a single mode fibers. So the misalignment tolerance is very high, so you can, if your fiber even move by 1 micron or 2 micron, you will still have very nice coupling efficiency. But the problem is the bandwidth is very limited. So this type of mode converter only works for, let's say, 30 nanometer or 60 nanometer at most. And also they are very critical to the angle. So if your angle slightly change, your 3 dB bandwidth can easily shift to the other wavelengths. This bottom example I just picked is some recent advantage, some recent advancement by IBM. So they're using this sub-wavelength metamaterial waveguide to couple the light externally from a single mode fiber to the chip. So they use this polymer waveguide that is kind of converting their 10 micron to the, let's say, to 3 micron, and then from 3 micron they use this metamaterial, sub-wavelength metamaterial waveguide. So the whole concept was that they can really package, or they can really do the very efficient packaging using the standard CMOS solution. So these are like a mode converter that already exists, but I just picked 3, but there's like many other mode converter that do exist, such as double layer taper or etc. I mean, because it's like for our case, we use mostly work with silicon nitride, and we generate frequency comb that has very broad broadband coverage. So we prefer this inverse taper. So I picked this example from a recent work with my colleague Junki Liu. We'll use this inverse taper that has a fixed height of 800 nanometer, but the waveguide is not rectangular; it's a trapezoidal. So there is some angle with respect to this one. So this angle is around 80 degree. So I picked the standard number such that you can already, when you do the simulation, you can compare the result with this paper. And the cladding material is silicon oxide. So the core is consists of the silicon nitride. For the simulation model, what I will consider is following. So we'll start with the source. That is a Gaussian mode. So we are not kind of designing a fiber based, like a lens fiber here, because if you really ask the manufacturer of these lens fiber, they will tell you that this mode has a mode field diameter of 3 micron or 2.5 micron. So we can really just pick a Gaussian source from the Lumerical that has a mode field diameter of 2.5 micron and use as a source. And then we inject this source inside this taper that has this initial taper width. If you see in the last slide that the top part, that is the part that has a smaller width as compared to the bottom one, is our initial taper width. Then we inject this source in our taper to see like how the mode is propagating inside this silicon nitride waveguide. We'll try to vary different taper lengths to see the effect of adiabatic conversion, how the mode is converting from from 3 micron Gaussian source to fundamental mode of waveguide that we are trying to look. So this is like our bus waveguide that is coupled to microresonator. So that's like a silicon nitride waveguide covered with the oxide. So we will follow the same procedure that Jung-Q already told you, that we'll try to define the geometry, like our waveguide that consists of silicon nitride, our cladding that consists of silicon oxide. Then we'll define the source. As I mentioned, we will use the Gaussian source with the mode field diameter of 2.5 micron. That is kind of standard if you buy this lens fiber from either from Nanomax or this Nanonix or from Aussie Optics. And then we'll try to look. We will put some different monitor here to see how much light from our source is coupled to this waveguide. And here we'll use some mode projection because we are kind of interested in the fundamental mode. We are not interested in the higher order mode of our bus waveguide. Good thing is that Lumerical already do this thing for us, but we just need to put like 1 or 2 monitors, and we can already know that how much light is coupled to the fundamental mode. Also, I think we really don't care too much about whether we really because we are using this taper, and the mode that is propagating through this taper is only fundamental mode. So we'll not excite any higher order mode. So we really don't need to. I mean, even if we just see at the normal transmission, that can give us like a good estimation how much light is transmitted from this point to the endpoint. And okay, so this is like our simulation region. So that's kind of a simulation model that we're going to consider today to design an inverse taper that can couple light efficiently from a 3 micron or 2 micron source to this bus waveguide. So now I will move towards this Lumerical software to tell you, I mean, to just give you how we can build this whole model that I showed in my presentation from the scratch. So if you open this this model with the name of PPT template, so everyone now is working fine for everyone. It's okay. It's perfect. So the inverse taper is already defined. So if you see here, okay. So if you see here, if I move toward the x-axis, okay. So my length is along the x-axis. So if I can draw this structure here. Just to give you like a bit of understanding. So this is along x-axis. So my length of taper is along the x-axis, and the width of taper is along the y-axis, and the height will be along the z-axis. Okay. So if I just move along the x-axis now, you will see like the taper is getting bigger. So it's mean like we have like a linear taper. Okay. So if I move further, you see like it's becoming bigger and bigger. At one point you will see like the taper is fixed. So that's our bus waveguide. Okay. Sorry? We are using some scripting here. So that's we can discuss in the exercise session, because that's why I gave you like something already made inverse taper here. Okay. So if you see here afterwards, this is fixed now. Okay. So that's our bus waveguide. Okay. So if I try to see like what kind of parameter we selected. Okay. So index is 1.98. It's like close to the silicon nitride. Okay. The taper width is 50 nanometer. That's the initial taper width that I told you already on my slide. I set it to 50 nanometer. Taper length 300 micron. So let's set it to around 100 micron, such that we can save some time for simulation. And the waveguide width is 2 micron. So that's like a standard we use for silicon nitride process in our group at EPFL. And the total length you can reduce to 500, because 700 will be too much for this doing the simulation here. and the height is around 800 nanometer. That is 0.8 micron, as I mentioned in the slide. And that's like a number of points. So when you set it to 500, then your structure will be very fine, and you already saw some glitch in your software. Okay. So there is like a small script written here. So if you see here that we define where is our x, from where our structure is starting, x minimum is equal to 0, x max is like, x max is the how long is our overall taper. That I define up to, I think, 500. So that should be 500. And similarly, there's height and width is defined here. So during the exercise, if you have some question, you can ask about this script. Okay. So now we define the silicon nitride part. So if you really want to see like you can press this one such that everything is in focus and you can see it, and then you can refocus it afterward.
What do you do next?
So now I'll try to add the oxide. So if you go to structure, because for the oxide we don't care, because you have a nitride, it has sidewall angle, but for the cladding, you can just put a rectangular waveguide. So I will put a rectangle here, okay, and now I need to adjust different parameter for this one. So I add it. I know because my structure is starting at 0, I will just put 0 as my minimum, okay, and the maximum of this nitride waveguide length is 500, okay. Okay, you can keep it like 10 here for both of this one.
Where do you find the rectangle?
Sorry?
Where do you find the rectangle?
If you go to structure, let me just do it one more time. If you go to structure, you will see a rectangle here on the second one. Okay? Yeah. Perfect. It's fun for everyone? Yeah, because for cladding we really don't care that we need to make a trapezoidal shape. Rectangle is fine. Okay? Okay, for material you can define silicon oxide, because our cladding material is silicon oxide with this one, okay? You can define in the material a silicon oxide and this pellet. So it's already have this, the refractive index is already built in with as a function of frequency or wavelength, like normal dispersion relation. Rotation, I think you are not considering. So if you want to rotate your structure, you can add some number, but we are not considering these things in current simulation. Sorry? Yeah, sure. Yeah. Yeah. Because for you, the cladding is kind of infinite, so you can make it. I'm sorry.
I had a question actually.
Yep.
So your taper is actually having this kind of triangle shape, but
yeah.
it also has some weird profile. But it's actually, I've seen you make a triangle from cubes, and there is some sort of discretization. So what's the rule of thumb for this? Like how you should discretize your structure in order to not have numerical artifacts?
So that's really depend on the number of points I show you in the script. So it's kind of work as like you're making a shape in the SolidWorks. So you define your equation, and then you try to make like a 3D structure out of it. So you try to converge. Yeah. If it works, you don't increase. I think you make an equation for a shape, and then you make a 3D structure out of it. So yeah.
So which material do you need to use?
Sorry?
Which material do you need to use?
Silicon oxide.
Oh, glass.
Yeah.
Glass,
Okay, it's done for everyone? Cool. Okay. Only one thing, you need to move this guy up. Move up, yeah. And now you can really see the nitride on top of oxide. Okay, so they're like very well listening. So the question you were asking, so you see that our nitride is already have this angle, you know. So if you see here, so this the structure that I shown in my presentation. So it is like a sidewall angle, and then you have this this thing. Okay,
Okay, yes.
it's perfect. Yeah.
Because also if you zoom on the 3D view, yes, you
Uh,
see something a bit different. So it's really a triangle if you turn it right.
Yeah, but I mean, okay, I'm not very familiar with this 3D view handling of this software. Okay. So the next thing is, like, I think as Jung-Chu mentioned, is the defining a simulation region. So we'll define a simulation region. You go to the simulation, this point, and just press this guy. Okay. It's fine for everyone? No? Okay. So I think as Jung-Chu mentioned already, that we need to keep this simulation region as small as possible, because you already saw you face some problem with even just running the software. So we'll try to make this simulation region as small as possible. Okay, here. So this background index mean, like, wherever the material is not, then it will count this thing as a refractive index of 1. So let's say if this region will be counted as a refractive index of 1. Okay. Other than your material, where you define your refractive index, it will be, the refractive index will be 1. Okay. Then simulation time. Okay, so we're just going to put like a 5,000 femtosecond. So your simulation time should not be too small, such that your mode that you're injecting from here doesn't reach till this point, and it should not be too much big, such that you are just keep running your simulation. So I think we found this number that work really great for our simulations, which you can just put like a 5,000 femtosecond. Okay. And then we have to define the region. So we'll start from, if you remember that our waveguide was starting at 0, exactly at the 0. So, but we will keep our simulation region, like say from -5 and 270.
500 was the length.
Yeah, but I think 70 micron is more than enough. When you more propagate to like a 70 micron of your bus waveguide, is more than enough to calculate your analysis. Okay. Because once you really excite your fundamental mode in your bus waveguide, it's perfect. So it can propagate without any issue. Yeah. For Y1, we know that our width is around 4 micron. So we can go to, it's 2 micron, sorry. It's 2 micron, so we can go to 4 micron. And for height is around 800 nanometer, so I can go to, let's say, 2 micron. For the simulation region, it should not be just touching your waveguide. It should be slightly bigger than the structure you're looking. Okay. The rule of thumb is like to have 3 times than your structure. Let's say if you have a structure of 3 micron, then it's much better to have a simulation region of 6 micron or 9. Sorry. For the mesh setting, I think Jung-Chu already told you this thing that. We need to keep it as small as possible. Okay, so let's say we go with 1. Okay, but to really check your just simulation model, is much better to keep it 1, and then you can later increase it once you really get some result. Okay, for the boundary condition, I will just go back to my presentation. So if you see here that we have a trapezoidal waveguide, it's this one, okay, and we are considering the TE polarization, okay, and the only boundary condition we can use is that our structure is like is symmetric around this axis. So this is our boundary, and if we see the TE, this is kind of perpendicular, so we have to use the antisymmetric boundary condition inside the Lumerical. So this is a slide I picked from the Lumerical website. So for the Y, I will use the antisymmetric boundary condition, because your polarization is perpendicular to your boundary. We'll not use the stretch, rather uniaxial, as because stretch you really try to look for the broadband source, but here we will just look at the a Gaussian beam with the center wavelength at 1.5 micron. Okay, and there's some advanced option like auto shut off, so this will turn off your simulation before certain threshold. So Yep. It's going fine for you guys? Okay, perfect. Okay. So you see now your simulation region is defined. It's fine? Okay. Okay. Now we have to put the source. So first we put our waveguide structure, then simulation region. Now we have to put our source. Okay. As I mentioned that it's very difficult to design a lens fiber. So it's much. We know from the manufacturer that the mode field diameter of this lens fiber is 2.5 micron. So we can just pick a one Gaussian source, set the mode field diameter around 2.5 micron as our source. Okay. So if we go to the source section, there's an option with the Gaussian. Okay. Now we can edit this thing. Okay. Should I repeat one more time?
Oh yeah, well, yeah, opening the source.
Okay. Now if you remember, we will put our source somewhere here and it will be injected along the x-axis. So we need to change our injection axis along x-axis. So we are injecting our source along the x-axis. Okay. Oh, okay. So we'll put our source here and it will be injected along the x-axis. Okay. Direction is forward and this polarization is 0 is TE. Okay. If you define 90, then it will be TEM. So we are going with the TE polarization for our first simulation. Okay. So we just now for the geometry, you want to place it like we know that our waveguide is starting exactly at the location x is equal to 0. Now we can place it slightly far away, like -2 on the x-axis. On this one, we can just say like it's fine now. So I just changed like the y span and the x span of this thing. I don't think so. It has too much influence there.
X coordinates they are blocked.
Yeah, you just need to add those location of because x is blocked because you're injecting along the x-axis.
Okay.
That's why. But for x, you just need to add value here, at the first one,
Okay.
and then it will be automatically set there. Okay.
Yes.
Okay. Perfect. For the frequency, we'll just use 1.5 micron. That's like a standard telecommunication wavelength. So we are not doing any broadband source. We are just selecting a Gaussian source centered at 1.55 micron, 1550. And we can remove this option, optimize for short pulses, because we are not doing any short pulses. And then the beam option. Here we can decide as I said, like the mode field diameter is 2.5 microns, then the radius will be 1.25. Okay, and if you see that I put the source at -2, then the distance from the waist will be -2. Okay. Okay.
I have a different plot on the right. I have a line. What is that?
Kanish?
All right.
Did you select the wavelength or frequency? If you go to frequency, you selected there, optimize for this one, geometry, and if you go beam option now. Okay. Now it's there. Okay, perfect. Okay. So now we have a source. If you see, the source is injected along this axis. So this arrow is showing the injection axis, and these arrows are showing the polarization of your source. Okay. Okay. So we have the simulation region, we have the source, we have our structure. What left is the monitor. So we really need to monitor different like a mode profile or the transmission. Okay. So first thing, as I think my colleague Junki already mentioned, that we want to see how the transmission profile looks like. Okay, and the mode propagate from this position to that one, how does it look like, and how the transmission profile look like. So for that one, we will select the monitor. This one, frequency domain power and field and power. So you select this one. Okay. No, you really need to define from -4 to 270, or let's say 265 within your simulation region. Okay. And for Y, you can really say 4 to 4. Okay. Yep. Okay. I think data to record, I mean, you will say like it will record E, X, E, Y, E, Z, but we are kind of more interested in the output power. Okay. These other option you can leave as it is in the spectral averaging and apodization and advance as well. So it's fine for everyone? Okay, that's cool. Okay. Now we are going to put the.
Now it monitors the whole.
Yeah, that's like whole. Like if you really see your, just see like your if you have a chip and you're just trying to look from the top how the mode is propagating from your fiber to the. To the bus waveguide. Sorry, there's some issues here. It's perfect. Okay, cool. Now for the transmission. So we really want to see that if we are injecting this mode here, what will be the transmission at the bus waveguide. Okay. So I will add this again, this same monitor. Okay. I will say. Okay. You can also change the name. Sorry, I didn't mention this thing. So if you press F2, I mean, as I think Johan mentioned this thing, this shortcut. So you can say this thing for the transmission. So you can call this thing transmission. Okay. So I call this thing transmission. Add it. But now you're not interested looking from the top, but you really want to see the mode profile. So you have to put it along the x-axis. So this one should be 2D x normal. Okay. And you want to place it at. Our whole simulation region is 270, 260. It's a good number. 4, 4, 3, 3.
Why is no? Oh.
It has to be 2dx normal, not the 2z.
Yeah.
Okay. Because previously we were looking from the top, so that was the your monitor was perpendicular to the z-axis. Now it's perpendicular to the x-axis. Okay. Works for everyone? Okay, cool. Okay, so this particular monitor, the one that you see here, that's just tell you to try to integrate the mode field, you know, all the mode field within this spatial region and give you the transmission. So it doesn't, this guy doesn't care about if whether you have a fundamental mode, higher order mode, or something else. So what it will do, it will calculate the power and normalize with respect to your source. So the transmission you will get, it will be normalized with respect to your source. So if you're injecting from your source is 1 and the power you get here is, let's say, 0.8, then you have a like 80% transmission. But this thing, there's always something. This guy doesn't take into account whether you're looking for fundamental mode or higher order mode. So if you really want to do like look into how much power is transferred into your fundamental mode or to higher order mode, then you have to use another monitor known as a mode expansion. So this will do the mode expansion for you. So you can call this thing as a, okay, I'm pressing the wrong thing, TE 00. So we added this thing. We need to place this thing on top of the other monitor where we placed our previous one, transmission one. Okay, thanks. 2dx normal, it was 265.
Yeah.
Thanks.
260.
260?
Yeah.
Okay, thanks. And I say 4 minus 3 minus 3. Okay, looks, and now we go to this another section of mode expansion. We can select the fundamental mode, fundamental TE mode or fundamental TEM mode directly. So it will calculate automatically from us the region we gave to the monitor, okay? But you can also do the user selection. So if I do the user select mode, and say, I mean now it's like a FEM simulation, you calculate modes. And I pick this one, the first one, that is a fundamental mode for me. So that's like my bus waveguide structure that you see here.
Did you get the list?
Okay, so I go cancel. You go user select from here, select mode. Okay, so just say you calculate, okay, calculate the modes. Okay, so you can just select this fundamental mode because it has a TE polarization with 100%. Okay, and you need to add this monitor. So the monitor we need to add. Even mine is stuck now.
Oh, I cannot select the mode.
Why?
It's grayed out.
Can you flip it? Okay. Okay, so you said say, okay, that's okay. I think your simulation. Can I just check your? Can you bring this guy down? Cancel. Your geometry. 2dx normal 260 looks fine, but why it's not working? Okay.
Nice and uniform.
Can I go a bit up? Okay, so I'm not a Mac user, so user select.
Yeah, me neither.
Oh, you're also not. But why this guy is not showing 4 here? Okay, so there is something, but it was working fine for you. Okay. Okay, I will come back to you later. Okay, so I think there's some problem with the union of your structure because it's just seeing one structure. It's not seeing the waveguide or the core or cladding. So you're just seeing only one structure and it cannot calculate the mode for you. Okay, so there is a problem with your structure. Okay, so then we need to add this transmission monitor we used last time here in this one. So that will really now give us the transmission of fundamental mode. Okay.
So just make the projection of your.
Exactly, that monitor to the mode expansion. Yeah. So you just need to press this guy and then you will have a transmission here. Okay. So yeah, I think we have everything ready now. So that's how like a similar thing these things work. So if you see like a simulation memory and the memory report is asking me like 500 MB and like so if you select here, you can already check your simulation and then it's going to give you the how much simulation here. Okay.
Yes.
Okay.
Then can you press run?
Does it estimate the calculation time also? Or not?
I don't think so. Because the problem is that you already gave auto, it will start like it will give you like 3 hours initially, but then you also gave an auto shut off level. So maybe in between these 3 hours you reach auto shut off level, the simulation will be closed. So it's difficult to predict the simulation time. So yeah, I mean for me it's 23 minutes. So I think for you guys it will be much more because I'm using a simulation computer. It has like a, yeah, but it has like a lot of cores. So you have everything running in parallel. So I'm most probably will be using more than 75 or more than 70 cores at a single time.
I don't know how it's hard.
For you it will be much more than this one.
8 minutes.
Yeah.
8 minutes.
Yeah.
8 minutes. 8 minutes. 9 minutes.
Okay.
For me, there is no.
We can use your computer as a simulation computer next time.
Which simulation?
Mine doesn't even.
It's the old one.
That's really smart.
Okay. So I will just quit this simulation, and I have also uploaded one file with everything already simulated. You can now open this other file. This file that I already uploaded. So this thing is simulated. So we can already now start seeing the result here. So there will be, I uploaded 2 files there. Okay. So now you can open the other file there. So it has like a TE-EXP. So now you can open this file with the ending TE_EXP. So you open a file with the file ending name TE-EXP.
Yeah. Underscore T not.
Sorry?
There is another one underscore T not.
No. Just use TE_EXP. I have to be quick now, huh? No, because the exercises time has to be shrink, so quick now.
You're right on time.
Okay. I'll just give an overview in presentation and then I will stop it. Okay. So the very first thing we want to see how the field look like. So it's also hanging for me.
Because you're running that also in parallel.
So yeah. Oh yeah. So thanks for reminding. I think I quit. Yeah. So you can already see here, and you can change the different parameter to log scale. So that's already tell you like how your mode like really propagated from this point to your bus waveguide. And if you really want to see the transmission now, what will like this has same thing that already mentioned you, like everything was implemented using this model. So if you see the transmission, so it is around 86%. Yeah, but that's really good. Yeah.
Okay.
Usually this inverse taper they have now the highest one is 45%, the total one.
Okay.
That's one. But this is only through one taper. So in reality, you have a structure like you have one taper on this side as well. So what happened? You have to really square this number, and then it will give you the total this one. So this will, I think, at the end will give you like 65% total coupling efficiency. Okay. So if things turn out and you don't have any scattering losses in between. So I hope that you guys can now make a very basic model in Lumerical yourself. Okay. Okay, cool. But we also provided you this model where you can really try to change different parameters and do simulation at during your free time.
What is your fundamental mode percentage?
That's already a fundamental before.
No, I mean like expansion. What is your expansion really? Can you show the expansion? Mode expansion.
Mode expansion, sorry? Like how many modes are there, huh?
So okay, 86% is
Yeah.
already into that.
Yeah, that's already being there. So yeah.
Yeah, and how much is it for the total?
Total, I have to really check this number, you know. You can find this number there, you know. I mean in this there should be somewhere you can find the total one. I think here, like total one here. like you get a lot of drop menu here, and you can see like total one, and then how much is forward, and I think the forward is already how much you couple into your fundamental mode. Okay, so we come back to this presentation now. So the model that we simulated is like have a only one taper. So in reality, you have like a bus waveguide, and you again have a one taper on the other side. So the transmission you get, you have to multiply this thing. Let's say 0.86. You need to multiply these two numbers, and you will get your total transmission from this side to the other side of the chip. Okay, because you have two tapers. And here we kind of take assumption that everything is ideal. So you can just try to copy paste and bring to the other side, and things will be similar. Okay. So yeah, I mean, first what we did, we tried to define our like the things we did for building the model. We tried to define our silica using the structure. Nitride was defined using this script that you can already find in the template file. Afterward, we defined the simulation region. We use this PML boundary condition, and for the mesh we use the very coarse mesh size. And then this thing that we mentioned, that how we can reduce the simulation region. So if you have a rectangular structure, you can reduce your simulation to 1/4, because by using a symmetric or anti-symmetric boundary condition. For the trapezoidal, for our case. Yeah.
What actually is the accuracy difference that you get there? Because when the mode transitions are all very adiabatic, it shouldn't make a difference.
No, I think it will, but if it's depend like what is the length of your taper, huh?
Yeah, exactly. If it's very adiabatic, it shouldn't.
Yeah, sure. I mean, when you go more than 100 micron, then I don't think so. It's.
Second question I have is, what's actually the mathematical definition of adiabaticity in this context?
Mathematically, how I can define this thing.
What's the condition you have to fulfill, basically? I mean, I also know if the taper is longer than 100 micron, it shouldn't make a difference.
It's more like, I think it's again like your mode overlap, in your bus waveguide. The more that is like really changing its shape inside the taper, and then the mode in your bus waveguide, if you try to overlap them, the better the overlap.
So the change in effective index per unit length
Exactly.
is smaller than 1.
Symbol.
The second derivative has to be less than the first derivative times. Yes. Yeah? Probably. No.
Yeah. You have some question?
So that's a good question, actually. Yeah, there should be a mathematical criteria.
Yeah.
That define what is the designable.
I guess you checked whether or not the Comstar solution just calculating the evanescent mode that they're using the overlap integral and how it compares to numerics.
But this is the similar segment.
Yep.
We basically just calculate what overlap with the.
But he solved the full propagation. I mean, he propagates the mode from left to right, yeah.
Yeah, but the Comstar also do the same.
No, you can just calculate the mode using the dispersion mode, basically, and overlap this with the Gaussian mode.
There is a sudden boundary here.
Yeah.
So you don't think about the reflection.
The only thing is like adiabaticity.
Somebody at some point checked it.
Yeah, I don't know what does usually there is no mathematical formula of adiabaticity. To me, it's like a measurable. So basically, you only measure the adiabaticity or not instead of actually calculate that adiabaticity.
Yep.
So usually you always simulate and then you look at the transmission mode and you compare with the input mode and see this is the simulated adiabaticity. But it's not like give you parameter that you calculate with a strict formula. So I think that's actually, so there should be, I agree that there should be a mathematical criteria that billing allows you to estimate the adaptivity. But for integrated point of view, that actually just in order to just make it infinity long, and that adaptivity always approaching one.
Yep.
It's always kind of a balance between the adaptivity and the footprint of the device.
Yeah.
Okay, a simple question, where is your 14% of energy? Where is the gap?
Okay, so you're first of all, I mean, like your refractive index is different. Like you're coupling from air to nitride, so some light will get back reflected. You're losing some of there, and also your mode is not perfectly Gaussian, but it's like a trapezoidal, so overlap is also not very good. So we are losing some of light there as well. So, yeah.
And what happens if you make the taper not
Linear or some other shape? I think.
no, not diabetic. Like if you leave 15 micron taper.
Or then you have like a very abrupt transition, and then you will lose quite a bit of light there for sure.
And is it like back reflected or is it radiated?
I think radiated, yeah. It's radiated, huh? Yeah.
You can check with the paper that we write that actually does a propagation profile, right?
Yeah, that's I'm going to show you.
The guiding light,
Yeah.
the radiation.
So yeah, then we selected the source. So as I mentioned that we use this fiber mode with the 2.5 micron mode field diameter. We only looked at the TE polarization, but for your exercise session, you can really try to look for the TM polarization. Then we just defined that the wavelength, the mode is centered around the telecommunication wavelength 1.55 micron. Similarly, the injection direction, etc. Then we put different monitor to really get the total transmission or the transmission into our fundamental mode by using this built-in mode expansion. So Lumerical really do this thing for us by doing the mode projection. You can also look for effective index or some other stuff if you try to explore the Lumerical software. So yeah, I mean, I think the result that at the end I showed, like you can already see like how the light is propagating from the source that has a mode field diameter of 2.5 micron to the bus waveguide that has width of 2 micron. So the initial taper width here is also kind of I think 100 nanometer approximately. So you can see like at this point your mode field is I mean, you can already guess from here like TE mode is not very well matching with the mode of your taper that is at this point. So you will lose bit of transmission here, and then we kind of adiabatically transform this mode into the bus waveguide mode. So that's why we overall we have like a transmission of 70 or 60%, but only per taper. The overall transmission will be still less than 50%. Okay. I have to check the paper, so I think it's log scale for sure. Yeah, it's a log scale. Yeah. This is log scale. Yeah. Yeah.
Yeah, because the linear scale is
Yeah. We will see. Yeah. Yeah. You can also adjust the numbers, in your color bar. So yeah, so as I mentioned, like for the taper, we really need to adjust the taper width, So here I didn't show you like how we can do the sweep. So if we go back again, sorry for interruption one more time. So here's Lumerical has built in, so you can like put a sweep parameters. So if you go here, optimization and sweep, you will find this menu with the create a new parameter for sweep. Here you can add it, and you can add some new parameters. And with respect to these parameters, you can look for different functions you want to see. So you can put function, let's say you want to see transmission, or the full flow of field from input to the bus waveguide, or the effective index. So you can define the parameter here. So you can do the sweep. So you make a model, you pick one number. Let's say you want to sweep the width. You want to sweep from 50 nanometer to let's say 5 micron. You define the number of steps, and then you can just run the simulation one time, and you will get the result for all the sweep together. Sorry. So that's what we did here. So that's the result we published in our paper I think 2 years ago in optics lecture, where we try to sweep the taper width from 50 nanometer to 300 nanometer, and you can see how the coupling is really dropping here. So the trend is like you want to make your tapers as small as possible to couple the light from your input fiber to the bus waveguide. So you can see like we achieve around 80% of coupling in the simulation, but in reality you see like the coupling is even less than what the simulation is expected. But the trend is matching very well, that the transmission is going down. So that's what you can really get from your simulation. So once you get your trend from your simulation, you can really verify your experimental result, what the model you built in the Lumerical. So for the exercise session, okay, if you guys have any question related to the how to make a model or something, yeah.
So what's the reason that as we decrease the taper width, we are getting higher efficiency?
Your mode is getting bigger and bigger, and it's overlapping very well with the input fiber mode.
No, I mean, actually, we decrease the taper width at this coupling region, right?
Sorry?
It's narrow, and we are dropping like this, right?
Yeah.
And what's the reason if we decrease this width, we are having higher efficiency? Is that we are decreasing the back reflections of the wave that are coming from?
There will be a certain point where your mode will like not cannot really. I mean, you start radiating because of the. If your taper width is too small, then I think it will not support anymore, and then you will have like all the energies radiated. So there's a certain taper width that you can physically make such that it can support certain eigenmodes. But if you go too small in terms of taper width, let's say 5 nanometer or less than 5 nanometer, then all the energy will be radiated because of the strong potential difference somewhere.
Let me answer your question. So if you launch a Gaussian mode, the Gaussian mode by nature is divergent.
Yep.
Yeah. And
Yeah.
then your input taper is actually confined structure. So
Yep.
basically, if you want to guide this mode, the first thing you need to make sure is that your confinement is stronger than your divergence. If you make your taper really, really small, even though that your mode matched very well, but that the waveguide is too small, the optical confinement is too weak to overcome divergence of a Gaussian beam, then your coupling will not be good enough.
Yep.
So this is the reason why there's always an optimal taper width, such that the optical mode mismatch is okay. Simultaneously, the confinement of the taper is able to overcome the divergence of Gaussian beam.
This is fine? Okay, cool. Anyone else? So yeah, so for the exercise session, so what you have to use, what you guys have to do is to really do the model we built for the TM polarization. So you have to change the, I mean, I already gave you some hint here such that you can quickly change the same model that we built here. So you can really change the polarization of your source, and now you have to also think about how the boundary condition will change, because here we were like anti-symmetric, but now what will happen if you inject a polarization that is going along this direction? So you have to change your boundary condition in your model, and similarly you have to really change your, because we already use the TE mode in our monitors, so you have to really change your now to change back to the TM mode. So you have to change some stuff in your exercise, like the model that we already provided, and then you can simulate one. And similarly, I think the question asked by Johan, so we'll see like how the impact of taper length on the transmission. So just keep like a 20 micron of taper length, and then see, then try to change the taper length to 100 micron, and you will see like how it will affect the transmission, because your mode is not adiabatically transformed from your fiber to your bus waveguide. So the length we're talking about, this length, okay. So that's kind of two exercise that I put for this fiber chip coupling session. So yeah, with this one I will just like to end this session, and if you don't have any further questions, so I can just stop here. Yeah.